Welcome back to Operating Systems Crashcast. I'm Victor, and with me as always is the brilliant Sheila. Today, we're diving into Section 7.5, Deadlock Avoidance. But before we start, Sheila, could you briefly explain what a deadlock is for our listeners who might be new to the concept?
Of course, Victor. A deadlock is a situation in an operating system where two or more processes are unable to proceed because each is waiting for the other to release a resource. It's like a traffic gridlock, where cars can't move because they're all waiting for each other. Now, let's talk about how to avoid these situations.
Great explanation, Sheila. So why don't you kick us off with an overview of what deadlock avoidance is all about?
Gladly, Victor. Deadlock avoidance is a proactive approach to preventing deadlocks in operating systems. Unlike deadlock prevention, which restricts how resources can be requested, deadlock avoidance requires the system to have additional information about which resources a process will request and use during its lifetime. The key idea is to ensure that the system never enters an unsafe state where deadlock could potentially occur.
That's a great introduction, Sheila. Let's break it down further for our listeners. Can you explain what we mean by a safe state in the context of deadlock avoidance?
Certainly. A safe state is a state in which the system can allocate resources to each process in some order and still avoid deadlock. In other words, there exists a sequence of processes where each process can complete its execution without causing a deadlock. On the other hand, an unsafe state is one where we can't guarantee that deadlock won't occur.
Excellent explanation. So, if we can keep the system in a safe state, we can avoid deadlocks. But how does the system decide whether a state is safe or unsafe?
That's where the concept of a resource allocation state comes in. The resource allocation state is the current state of resource allocation to processes. It includes information about available resources, allocated resources, and the maximum demands of processes. The system uses this information to determine if granting a resource request would lead to a safe state or an unsafe state.
I see. So, we need an algorithm to make these decisions. That brings us to the famous banker's algorithm, right? Can you explain how it works?
Absolutely. The banker's algorithm, named after a banker's strategy for allocating money, is used for deadlock avoidance. It consists of two parts, the safety algorithm and the resource request algorithm. The safety algorithm determines if a state is safe, while the resource request algorithm decides if a request can be safely granted.
That's fascinating. Let's use an analogy to help our listeners understand. Imagine a bank with a limited amount of money to lend. The bank wants to ensure it can meet all its commitments without running out of funds. How would this relate to the banker's algorithm?
Great analogy, Victor. In this scenario, the bank represents the operating system, the money represents resources, and the customers represent processes. The bank, OS, needs to decide whether it's safe to grant a loan, allocate resources to a customer, process based on the current financial state, resource allocation state, and the maximum credit limits, maximum resource needs of all customers.
That makes it much clearer. Now let's dive into the safety algorithm. How does it determine if a state is safe?
The safety algorithm works by simulating the execution of all processes to see if they can all complete. It starts by looking for a process whose maximum additional resource needs can be met by the available resources. If it finds one, it assumes that process runs to completion and releases all its resources. It then adds these resources to the available pool and repeats the process. If all processes can run to completion in some sequence, the state is safe.
Excellent explanation. And what about the resource request algorithm? How does it decide whether to grant a request?
The resource request algorithm first checks if granting the request would exceed the process's maximum claim. If not, it then pretends to allocate the requested resources and runs the safety algorithm. If the resulting state is safe, the request is granted. Otherwise, it's denied, and the process must wait.
I see. So, it's all about looking ahead and avoiding potentially dangerous situations. Now let's talk about the practical implications. What are the advantages and limitations of deadlock avoidance?
Good question, Victor. The main advantage of deadlock avoidance is that it allows more concurrency than deadlock prevention methods. It doesn't unnecessarily restrict resource usage, which can lead to better system utilization. However, it does have some significant limitations. First, it requires knowing the maximum resource requirements of all processes in advance, which isn't always possible. Second, the number of processes must be fixed, which isn't realistic in many systems. Lastly, the banker's algorithm can be computationally expensive, especially in large systems with many resources and processes.
Those are important points to consider. In real-world scenarios, where might we see deadlock avoidance techniques being used?
Deadlock avoidance is most applicable in systems where we have a good understanding of resource requirements and where safety is critical. For example, in certain real-time systems or in resource-constrained embedded systems. However, in general-purpose operating systems like Windows or Linux, deadlock avoidance is rarely used due to its limitations. Instead, these systems often use a combination of deadlock prevention and detection recovery methods.
That's a great real-world perspective, Sheila. As we wrap up, let's recap the key points we've covered about deadlock avoidance.
Certainly. We've learned that deadlock avoidance is a proactive approach to preventing deadlocks. It relies on maintaining a safe state where all processes can complete without deadlock. The banker's algorithm, consisting of the safety algorithm and resource request algorithm, is used to make allocation decisions. While deadlock avoidance allows for more concurrency than prevention methods, it has limitations in terms of required knowledge and computational complexity. In practice, it's most useful in specific, well-defined systems rather than general-purpose operating systems.
Excellent summary, Sheila. That brings us to the end of today's episode on deadlock avoidance. We hope our listeners found this informative and useful, especially for those preparing for operating systems interviews. Remember, understanding these concepts is crucial for designing efficient and reliable systems. Thank you for tuning in to Operating Systems Crashcast, and we'll see you in the next episode.